Okay, we're going to take a look at experiment number 8, or op-amp experiment number 5. And this is a integrator differentiator op-amp experiment. So I've got circuit maker open, and what I'll do is I'll take and open up the first circuit. So we'll take a look at the integrator first. And here's the circuit. Blow it up. You can see it better. Let's put it about 150. There we go. Now, what we have here is a op-amp circuit where in the feedback path there's a 100 k ohm resistor, but there's also a 0.01 microfarad capacitor. So what happens is you notice that the non-inverting input, the red input pin 3, is grounded. We do have a feedback resistor, which means that we have the virtual ground concept, and we have the fact that there's no voltage differential between the plus and minus or inverting and non-inverting inputs, and therefore the signal input, which is a pulse waveform, is applied to the 10 k ohm resistor, and the current flows through the capacitor. And it turns out that that current that flows through the capacitor will take and charge the capacitor in a linear fashion. And as you'll see in a couple seconds, when we take and run this, what you get is a triangular wave shape out of it. So let me run it. And you might notice we don't need this guy over here. We have a green, which is the input, and the yellow, which is the output. So we have the oscilloscope here, and I'll blow it up. And as you can see, what happens is the green input, the square wave, which goes from -5 to +5 volts, takes and charges up the capacitor in one direction with a positive ramp or positive slope, and then when the signal goes down the opposite way, it turns out that it charges it up with a current coming back the opposite way, which causes the voltage to decline. So remember, we're going into the negative input here, so the op-amp flips over the voltage. So as you can see here, when the voltage is high, what happens is that the charge is causing the output to go down. When the voltage is low, we have the increasing ramp. So basically it looks like we have, and we usually take and look at the very end of the waveform, way over on this side here, because it takes about 5 pulses for things to settle down. And in the screenshots that I've attached, it turns out that we get about, I think, 12.5 volts for the change in voltage, and it turns out the time for that to occur, if I move A and B over here, time for that to occur is about 25 microseconds. So it turns out that I have the details in the screenshots, which you can blow up and see the measurements quite easily. So in about a 250 microseconds, we have about 12.5 volt rise. That'll give you the ramp speed of how many volts per microsecond or second is changing. And of course, it's symmetrical because you have either +5 or -5 volts. In the experiment, I believe I ask, I'm going to stop this. In the experiment, I believe I ask you to take and change the voltage. So if I edit this, and I think we're supposed to go from -3 to +3. I think that's what I ask. Okay. And I take and I run this now. what we discover is that, and notice how the waveform here tends to fall down towards the very end that's now stabilized. What you discover now is instead of being about a 12 volt, it's about more like an 8 volt rise for the yellow waveform, an 8 volt fall. The amount of time is still the same, 250 microseconds. So it turns out that, again, now we've changed the ramp number of volts per second will change due to the fact that the input voltage is changed. Okay, that's the integrator. Now, I'm going to take and load the differentiator circuit. And here's the differentiator circuit. And in this case, you'll see that, and let's blow it up. I guess we'll do the same thing with 150%. Oop. I think I did 500, which is way too much. Try to do it a little bit better this time. There we go, 150, okay. And here we go. So you can see the circuit here. And I can center it a little bit, there we go. Now I'm going to take in, before I run it, now you notice there's a capacitor in the input, and the feedback resistor is purely a resistor. And so in this case, what's going to happen is we're going to get this result. And down the, when I blow this up, you'll see it a little bit better. Now the input was the green waveform, and the output is the yellow waveform. So what I've done is I've applied a triangular waveform, and the triangular waveform has a certain slope to it, a positive and negative ramp, which are equal. And what happens is I get a output, yellow output, depending on the ramp slope. Here in this case, when I have a plus ramp slope, I get a negative output. When the ramp slope is negative, I get a positive output. Again, the signal is going into the inverting input. So in the screenshots, you get to measure this stuff, and I have the measurements done, so you can take a look at them. Not sure what, I don't think I changed anything, and I think that's it for the experiment. It's kind of a short one, but nevertheless, this circuit, if I have a capacitor in the feedback path, it will do integrating. A capacitor in the input will take and differentiate the signal. And so the first one, the integrator, turns a voltage into a ramp. On the second one, a ramp gets changed into a voltage. Okay, that's it.